Watch a fountain leap. Water climbs 3, 4, 5 meters into the air, hangs for an instant, then collapses into foam. It cascades down carved stone, fills basins, spills over lips, and rises again. The display looks alive, mechanical, restless. Your instinct says there must be a motor somewhere below the pavement, a pump humming in the dark, electricity feeding the show. But in Rome, in Tivoli, in the gardens of the Renaissance, many of these fountains ran for centuries before electricity existed. No motor, no pump, no moving part at all beneath the marble. Consider the numbers. The Aqua Virgo, an aqueduct completed in 19 BC, still feeds the Trevi fountain today. When it was built, there was no engine on Earth capable of driving water upward in a jet. And yet the Romans built jets. The gardens of the Via d'Este at Tivoli, laid out in the 1550s, spray hundreds of separate streams across a steep hillside, and they did it 300 years before the first electric pump was invented. So what pushes the water? The answer is deceptively simple and physically profound. The engine is the landscape itself. Somewhere uphill, a spring, a reservoir, or a diverted river stands higher than the fountain. Water in a sealed pipe, once it starts falling, carries the memory of that height as pressure. Release it through a narrow outlet, and it converts that stored height back into motion, launching itself skyward until it exhausts the energy of its own descent. The show is mechanical only in appearance. Its true engine has no gears, no fire, no current. It is gravity, patient and constant, pulling water from higher ground toward lower ground. And builders learn to steal a portion of that fall to make stone come alive. Every jet you admire is a debt being repaid to elevation. Every cascade is water surrendering the height it was given upstream. To understand how a valley of marble can breathe without a single machine, we must first understand the invisible currency that pays for all of it. Engineers gave it a name, head. And head is where the entire secret begins. Head is the word engineers use for the height of water, and height, in a sealed pipe, is pressure waiting to be spent. Picture a vertical column of water 10 meters tall. At its base, the weight of every drop above presses down. That downward weight, measured against the area it pushes on, is pressure. Roughly, 10 meters of vertical water produce about 1 atmosphere, near 100 kilopascals, or 15 pounds per square inch. Double the height, and you double the push. This is the essential trade. Vertical distance is not merely a measurement on a map. Inside an enclosed conduit, it becomes force. The source standing 30 meters above a fountain's outlet delivers 3 atmospheres of pressure at that outlet, and it does so without a single machine, simply because the water higher up is trying always to fall. What matters is not the length of the pipe, but the difference in elevation between the surface of the source and the mouth of the jet. A pipe can wander for kilometers, dip through valleys, curve around hills. None of that horizontal travel changes the head. Only the vertical drop counts. 2 reservoirs at the same height produce the same pressure, whether the pipe between them runs 1 kilometer or 10. This is why the Romans were obsessed with elevation. A fountain could rise only as high as the water that fed it, minus the losses of friction along the way. Give the water 40 meters of head, and, in theory, it wants to climb nearly 40 meters back up. Friction, turbulence, and the drag of the pipe walls steal some of that ambition, so the real jet falls short. But the principle holds. The height of the source sets the ceiling of the display. Understand this, and the paradox dissolves. There is no trickery. Water pushes because water fell, and it will push exactly as hard as its starting height allows. The genius of the ancients was not inventing pressure. It was learning to carry head across the countryside without losing it. And no one carried head farther or more triumphantly than the engineers of Rome and their rivers of stone. By the height of the empire, 11 great aqueducts fed the city of Rome, delivering water measured in hundreds of thousands of cubic meters each day. They stretched enormous distances. The Aqua Marcia ran roughly 91 kilometers. the Aniene reached about 87. And yet almost the entire length of every one was a channel of falling water, guided downhill by nothing but the patient logic of slope. The secret was gradient. A Roman aqueduct did not gush downhill like a mountain stream. It descended with astonishing gentleness, often dropping only a fraction of a meter for every 100 meters of travel. The Aqua Virgo, completed in 19 BC to serve the Campus Martius, fell so gradually across its roughly 21-kilometer course that surveyors had to hold the line to slopes measured in centimeters. Too steep, and the water would race and erode the channel. Too flat, and it would stall and stagnate. The builders threaded the needle between the two. To hold that grade across a broken landscape, engineers built the structures that still march across the Roman countryside, the towering arcades. The famous arches were not decoration, and not the aqueduct itself. They were pedestals, raising the water channel to exactly the right height so its gentle downhill slope could continue uninterrupted over low ground. Inside, near the top, ran the specus, a covered conduit lined with waterproof mortar, carrying the flow in darkness. When the water finally reached the city, it arrived still elevated, still carrying head. It fed into distribution tanks called castella, then branched into pipes, serving public basins, baths, and fountains. Because the arriving water stood higher than the outlets it served, it emerged under natural pressure, no pump required. The fountain in the street ran, because a spring in the hills, dozens of kilometers away, stood higher than the street. But hills and valleys do not always cooperate. Sometimes the land dropped away into a gorge too deep to bridge with arches. There, the Romans could not simply carry an open channel across the air. They needed a different weapon, one that sealed the water inside and dared it to climb. That weapon was the pressurized pipe. When a valley fell away too deep and too wide for even the tallest arcade, the Romans reached for a bolder trick, the inverted siphon. Instead of carrying water across the gap on stone, they plunged it down one slope, across the valley floor, and up the far side, all inside a sealed, pressurized pipe. The principle depended on head. Because the water started higher than it ended, it retained enough pressure to climb back up the opposite hillside, provided the far outlet stood lower than the source. The pipe dived into the valley, and at the bottom the pressure grew enormous, sometimes several atmospheres, as the full weight of the descended water pressed against the conduit walls. The engineers needed materials that could hold that pressure without bursting. They used lead, cast into pipes called fistulae, and sealed along their seams, and they used terracotta segments fitted and cemented together. On the great siphons, such as those at Aspendos, or the massive systems feeding Lyon and Roman Gaul, they sometimes laid multiple parallel lead pipes side by side, sharing the load, and set them into a masonry base called a venter that ran along the valley floor. At the low point of the crossing, the pressure was fierce enough to demand the sturdiest joints in the entire network. The Romans understood something that looks almost modern. Water in a full sealed pipe does not need an open downhill channel. It will travel uphill on its own, spending the head it gained on the way down, as long as no point along the route rises above the level of the source. Trap the water, seal the air out, and elevation alone drives it across the landscape. This sealed pipe knowledge, held under pressure and released through carefully sized mouths, is exactly what made pressurized fountains possible. The same logic that dragged water across a Gaulish gorge could shoot it skyward in a city square. Yet all of it, aqueduct and siphon alike, obeyed one unforgiving rule: you could never rise higher than your source. And that single limitation would one day torment the most ambitious garden builder in European history, a king determined to make water defy the very hill his palace stood upon. Louis XIV wanted a paradise of water. At Versailles, beginning in the 1660s, he commanded gardens studded with fountains, the Latona, the Apollo Basin, the Grand Canal, hundreds of jets meant to dazzle every ambassador in Europe. There was only one problem, and it was the oldest problem in hydraulics. Versailles sat on high, dry ground. There was no mountain spring standing conveniently above the palace to supply the head those fountains demanded. Without a source higher than the outlets, gravity had nothing to give. The engineers scavenged for elevation. They drained ponds, dammed streams, and built reservoirs on the highest ground they could find, storing water in tanks and towers so that at least some fountains could run on natural fall. They laid vast networks of pipe across the estate, but the supply was never enough. Contemporary accounts describe fountains switched on in sequence as the king walked the grounds, attendants signaling ahead so that each display leapt to life only as he approached, then fell silent once he passed, hoarding the precious head. The demand outran the elevation the landscape could provide. So Louis, engineers attempted something audacious. If nature would not raise the water high enough, they would lift it by machine. On the river Seine at Bougival, they built the Machine de Marly, completed in 1684. It was one of the largest and most notorious mechanical works of the age, 14 enormous water wheels turning in the current, driving more than 200 pumps through a groaning system of rods and chains. It hauled water up the hillside in stages, raising it roughly 150 meters to the aqueduct and reservoirs that served Versailles and the gardens of Marly. The machine was thunderous, temperamental, and hungry for repair, a monument to the sheer difficulty of defeating elevation by force. And that is the lesson of Versailles. Where nature refused to supply head, only brute machinery could substitute for it, at ruinous cost and endless trouble. The contrast could not be sharper with a place where nature gave everything freely, a hillside so steep and a river so obliging that hundreds of jets could run forever without a single wheel or pump. That place was Tivoli. "30 kilometers east of Rome, the town of Tivoli clings to a steep ridge above the Aniene River. In 1550, Cardinal Ippolito d'Este took possession of a former convent here and imagined something no fountain builder had yet achieved. A garden powered entirely by falling water, without a single pump. His engineers understood the site's gift immediately. The Aniene ran high above the villa's terraced slope, and the hillside dropped nearly 45 meters from the upper gardens to the valley floor. That vertical distance was the entire machine. Workers cut a subterranean channel, later widened into a tunnel some 600 meters long, diverting a portion of the river directly into the garden's highest reservoirs. From there, water needed only to obey gravity. It fed the 100 fountains, a stone avenue where dozens of spouts run in continuous parallel lines. It powered the oval fountain and the thunderous fountain of the organ, where falling water compressed air through pipes to sound actual musical notes, a hydraulic instrument driven by nothing but head. At the fountain of Neptune, pressure built through descending conduits erupts in jets that climb many meters into the air. Every effect traces back to the same source, the elevation of the diverted Aniene against the low outlets below. No boiler, no wheel, no horse. The steeper the drop, the taller the jet, the louder the cascade. Where Versailles fought its flat terrain and begged the Seine for lift, Tivoli simply accepted the mountain's generosity. The Via d'Este became the most theatrical water garden of the Renaissance, precisely because its builders read the landscape correctly and let elevation do everything. 4.5 centuries later, the same tunnel still carries river water, and the same jets still leap, unassisted, whenever the channel runs. It stands as proof that spectacle required no engine at all, only height, and the patience to route water down a hillside. But arriving pressure is only raw potential. The difference between a weak dribble and a soaring plume depends on what happens in the final centimeters, at the mouth of the pipe. To understand how the same head produces wildly different displays, we must examine the outlet itself. The head delivers pressure to the outlet, but the outlet decides what you see. Two fountains fed by identical reservoirs can behave completely differently depending on the shape and size of their final opening. The governing principle is simple. For a given head, the velocity of escaping water is fixed, but the form of the jet is not. Constrict the outlet and the same pressure produces a thinner, faster stream that climbs higher against the air. Widen it, and the water rises less but flows in greater volume, spreading into sheets and broad cascades. Renaissance and Baroque fountain makers exploited this with remarkable precision. A nozzle bored to just 8 or 10 millimeters, fed by a large supply pipe, sends a needle of water many meters upward. Enlarge that bore, and the plume collapses into a fat, foaming column. At Tivoli, and later at Versailles, craftsmen kept sets of interchangeable bronze mouthpieces, swapping them to tune each effect. Pipe diameter mattered just as much. A narrow feed pipe throttles the flow before it ever reaches the nozzle, starving tall jets of the volume they need. So builders sized the internal conduit generously and reserved the constriction for the very tip. Friction along the pipe walls also stole pressure, so the longer the run from reservoir to fountain, the weaker the arriving push. Engineers compensated by choosing higher sources or shortening the path. Beyond height, shape sculpted spectacle. Flat, fan-shaped slits threw water into shimmering sheets. Rings of tiny holes produced crowns and domes. Angled outlets crossed multiple streams into arches and lattices. The fountain of the organ used carefully sized channels to trap and compress air. Every visible form, the spire, the bell, the veil, the cascade, was engineered geometry applied to a fixed hydraulic budget. The water never changed its nature. It simply obeyed the mouth it was given. Yet before any builder could carve a nozzle or lay a pipe, he faced a harder question. How much water would arrive? How much pressure would survive the journey? And how high the jet would truly reach? Answering that, centuries before modern physics, demanded a hidden mathematics all its own. Long before anyone wrote an equation for it, fountain builders had to predict the unseen. How much water would a spring yield in a day? How much pressure would survive 20 kilometers of downhill pipe? How high would a jet actually rise? The Romans answered with experience and standardized units. Their engineers measured flow in the quinaria, a pipe of fixed bore, and estimated a fountain supply by the number and size of the outlets it fed. Frontinus, appointed water commissioner of Rome around the year 97, wrote an entire treatise cataloging pipe diameters and delivery volumes, exposing fraud where officials tapped extra water through oversized bores. His accounting was empirical, not theoretical. But it worked, because it was grounded in careful observation of what real conduits delivered. Renaissance engineers inherited this practical tradition and refined it by trial. They knew instinctively that a jet could never quite reach the height of its source, though they could not yet say precisely why. They compensated for friction by generous margins, and by testing full scale before finalizing a design. The true physics arrived only later. In 1643, Evangelista Torricelli, working in Florence, established that water escaping an opening moves at a speed governed by the height of the water above it, the same velocity a body would gain falling that distance. Torricelli's law gave the ideal. A jet fed by 10 meters of head leaves the nozzle fast enough to climb, in theory, nearly 10 meters back up. Decades on, Daniel Bernoulli formalized the relationship between pressure, velocity, and elevation, explaining why constricting a pipe speeds the flow and drops the pressure. Together, these laws named and measured what fountain makers had exploited by feel for 2,000 years. The mathematics had always been there, invisible inside every falling stream. The builder simply reached its results through patience, standardized pipes, and the humility to test. Torricelli and Bernoulli did not invent the behavior. They described a truth already carved into stone across Rome, Tivoli, and Versailles, which leaves one final question worth asking. Why did these silent, pumpless systems endure for so many centuries, and why do so many still run today? Consider what has survived. The Aqueduct, completed in 19 BC, still carries water into Rome and feeds the Trevi fountain, which pours out an estimated 80,000 cubic meters a day. The tunnels of the Via d'Este, cut in the 1560s, still divert the Aniene through the same hillside, and the same jets still leap. These systems have outlasted empires, dynasties, and every mechanical fashion that followed them because they were built around a force that never fails and never tires. Gravity does not break down. It requires no fuel, no attendant, no electrical supply. A reservoir set higher than its outlets will push water forever, as long as the source keeps flowing. That is why a Roman aqueduct could deliver pressure for centuries with only occasional cleaning of its channels, and why a Renaissance garden could run its 100 fountains through decades of neglect and still perform when the water was let back in. The machinery that failed was always the machinery humans added. The Machine de Marly at Versailles, that monstrous array of 14 wheels and hundreds of pumps, wore out, jammed, and eventually was abandoned. The parts that endured were the reservoirs, the towers, the sealed pipes, the components that simply held water high and let it fall. Complexity decayed. Simplicity persisted. This is the quiet lesson written across every site we have visited. The soaring plumes of Tivoli, the pressurized siphons crossing Roman valleys, the tuned bronze nozzles shaping veils of spray. All of it was theater performed by a single, patient actor. Height against depth. Source above outlet. The fall of water from higher ground to lower ground, converted into pressure, sculpted into jets, and sustained without a single moving part. We look at these fountains and imagine hidden pumps, secret engines, some concealed mechanism driving the display. There was never any such thing. The engineers of Rome, Tivoli, and Versailles understood the only power they ever needed was already flowing downhill. Every jet, every cascade, every silent, centuries-long performance points to the same unchanging truth. Gravity was always the engine.